Swayam Prabha. Digital India. Educated India.
In this module, we will look at the basics of building acoustics. We will talk about basics of sound, what fundamental things need to be understood before getting on with environmental acoustics as well as building acoustical design. So, we will primarily cover the basics of sound waves. We will talk about the decibel scale, which we commonly refer as dB. Sound is expressed in decibels, and the frequency spectrum, sound spectrum. Then we will look at the difference between sound pressure, sound power and sound intensity. So, as we know, sound is we deal with sound in terms of wave propagation. It is a longitudinal wave. We have compressions and rarefactions. Sound propagates as longitudinal waves. So, we have three parameters. One is a velocity, which is dependent on the wavelength and frequency of sound. At room temperature, typically it is around 340 to 343 meter per second. That is a velocity of sound. So, velocity as well as wavelength and frequency, they are related in terms of velocity is expressed as wavelength into frequency. So, what is sound? Typically it is a compression rarefaction. It is reaching you by propagating through a medium. We studied the bell jar experiment during our school. Sound does not propagate through vacuum. So, it needs a medium to propagate. The properties of the medium as well determines the propagation of sound. So, there is a sound source, there is a path and there is a receiver. It can be any source, it can be an equipment, it can be a bird, it can be a some event which is happening. Then there is a medium of propagation, typically it is air, we call it airborne, or when it propagates through the structure we call structure borne. Then it reaches human ear, we are the receiver, the ear is a receiver. So, three components, typical components are involved as far as sound is concerned. When this sound level exceeds certain threshold value, we perceive it as noise. Typically it is unwanted sound or undesirable sound. One person's sound can be other person's noise. So, the threshold typically varies depending on the source, depending on the path and depending on the receiver, the nature of source as well. Velocity of the sound depends upon the density of the medium as well as the temperature of the medium. Typically you need bulk modulus as well as density of the medium. Then you can talk about the velocity as well. There is a similar equation or expression which relates temperature of the medium with the velocity of sound. If you take simple examples, air at 0 degrees, density is 1.3, close to 1.3, speed of sound is around 331 meter per second. As you increase the temperature further, the speed of sound slightly goes up. Water, the density is different, it is higher. With higher density, the speed of sound increases. Take a material like concrete, 2300 kg per meter cube. The velocity of sound is pretty much higher than what you see in air. Dense material like metal, steel bar with a high density, then the speed of sound is really high. So, how do we express sound? We always talk about sound pressure, sound levels. Moment you say level, it is like a comparative term. We do not always, pressure is measured in pascals, but sound is not expressed in pascals. Typically you get to hear terms like 40 dB, 60 dB, 80 dB. So, these are like levels, not the direct pressure value. So, why do we need to develop this? First, when there is a wide range within which the numbers are varying. For example, in this case of sound which we are talking about, human ear can perceive quite a wide range of sound pressures. So, these kind of pressures, this wide variation in pressure, if you are expressing directly, it is a too much of long number, say it ranges from 10 power minus 5 to something like 10 power 3 in terms of pascals. So, we need a relative term to express. So, we always express quantity A and how much quantity B is in terms of relative, in relation to quantity A. So, if it is watts, there is a reference watt, if it is a pressure, there is a reference pressure. So, typically we are expressing it as ratio. So, then we can compress it and then scale it. So, in this process we are comparing, compressing and then scaling it. So, we end up with the decibel scale, that is what we call as dB, we will look little more in detail of this. As I said, the minimum perceptible sound levels vary somewhere as low as 10 power minus 5, 1 into 10 power minus 5 pascals, and it can go as high as more than 100 pascals. Of course, you will have hearing related problems. There will be short term, long term impacts if you are exposed to very high sound pressures. So, in order to simplify this range, we are expressing it in terms of decibel. The minimum audible or perceptible sound level is a scale, that is the scale A that we looked at here, quantity A. Then we are weighting it with respect to what the actual sound pressure is. For example, like a whisper, this is 10 power minus 3. If you express it in terms of dB, it would come somewhere close to 30 to 35 decibels. Like a jet propulsion, it will be around 10 to 20 pascals, can be higher, then it will relate to around 100 decibels. So, this is what actually we are doing in terms of converting pressure in terms of pressure levels. There are other terms like power and intensity, we will look at them. So, the basic thing is we have LP, moment you see L, this is level, P is pressure, and this is sound pressure level, which is equal to 20 log P by P reference. P naught is P reference, which is 2 into 10 power 5 pascals or Newton per meter square. This is a threshold of hearing at 1000 hertz frequency. We will talk more about frequencies. This is like typically a center frequency we call, or so we will look at frequencies more in detail, but this is what it means. This is a P reference, or the minimum threshold of hearing, below which you cannot hear. So, this starts from 0 and then goes all the way up to it can be as high as 140 dB or further more. You will actually start losing your hearing ability if you are exposed to very high intensity sound, or even intensities of around 110 dB for quite a longer duration. There will be temporary and permanent hearing impairments. I am going to show you one example. This is a physical measurement of sound that we took, and then we will proceed with what are the terms and parameters that we need to look at. As you see in this graph, this is sound pressure level. This is on 22nd October, it is 2014. What you see here is sound pressure level, there is dBA. I will come to this term A little while, couple of slides this would come. This is decibel sound pressure level, and what you see here is the time. So, this is somewhere from 5:45 to 6:05. This is 20 minutes recordings. Here you will see the following thing. This is like split into 20 minutes. This is the first 20 minutes, this is the second 20 minutes the same day. This is an environmental or ambient noise level recorded from a terrace of a house. What we find here, the sound pressure level somewhere varies around 55 decibels dBA here. Typically this is a suburban area, residential area, so there are not many extensive noise sources. It is around 55 decibels dBA. This is a CPCB, Central Pollution Control Board limit. I will show you the desirable limits that they have given, or permissible limits they have given. It is a CPCB limit here. So, around 550 there is a slight increase. There are certain high intensity sounds, certain continuously increasing sounds. I have highlighted some of them. As you go in time, there are lot of peaks, whatever I have shown in dots versus these stars. So, eventually if you see as the time grows, ideally as the time increases, like you go from 5:45, you go down to 7 o'clock, 8 o'clock in the night, ideally the sound pressure level has to come down, because the vehicular traffic would come down. After the peak hours it has to decay down. In this case what happens, there is a slight increase here, it has gone up above the limit which is prescribed, then it is going further up here. Here you are getting something close to 85 dB, around 6:45 it is touching 95 dB. You are also getting continuous levels here plus certain peak values. Around 7:30 you are getting sound levels as high as 120 dB. You are wondering what these numbers, what these things correspond to, which recording it is. It is a residential area, in a suburb, it is a Diwali. So, what happens here, it was quiet here. At this point people started doing the crackers. These are like continuously cracked. These are like rackets, specific instances of crackers. You get as high as 120 decibels. Some of these sounds are that intensity. This is what actually we actually do. This is a pollution control board limit. Every year you get to see these in newspapers, like this much level it went up to above the prescribed level. Of course you also have the air pollution levels going up. Just to touch base, we were talking about sound pressures and sound pressure levels. This is typically a man-made event, a series of man-made events. We are experiencing somewhere between 55 decibels to as high as 120 decibels in terms of sound pressure level, just to touch base of what it actually is. Now is this all enough if to understand about the sound pressure and sound pressure level, the characteristics of sound? Already we had a good indicator of how much variation the sound itself is causing, but sound is like a wide spectrum within which lot of variations can happen. So in order to get a closer look of the characteristic of the source itself or the propagating medium and the receiver characteristics, we need to split it into specific segments, so which we call as frequency spectrum. There are different types of frequency splitting. The simple thing or most common thing we use is octave band, that is 2:1. So you have a center frequency, for example you have a center frequency of 500, the next frequency center frequency would be into 2000, then it would be 2000, 4000. So typically our interest would lie somewhere between 31.5 hertz to 16,000 hertz, or some cases it would go from 16 hertz to 20,000 hertz or 20 kilohertz. This is typically for building applications. We refer from 63.5 hertz on the lower end, that is low frequency. It can go as high as 16,000 hertz, but mostly we stop around 8,000 hertz for our specific observation. How do you split these octave bands? There are, as I said, different types. This most commonly used is octave band. If you want to further split it up, you can split it up to third octave band. So each octave gets split into 3. I will show you more details about it. So using these simple relations, you can find out n is the which octave it is. This is upper limit and lower limit of the spectrum. Then if you want the center frequency, when I was talking about 500 hertz, 1000 hertz, these are center frequencies of bands. So if you want the lower limit from the center frequency, you can find the lower as well as the upper limit. So what is all about this octave and third octave? Let us start from say 31.5, we will go up to 16 kilohertz. So this is one band. In this band the upper limit is 22 to 44 hertz. If you split that further into 3 octaves, so you have 1/3 octave band where 25, 31.5 and 40. So 3 center frequencies are obtained. Then the next center frequency is 63, that is this into 2, which we saw earlier. This is single octave into 2. Then you get this, you can split it further into 3. Then you have 125, all the way it goes to 16 kilohertz. Now by splitting the single signal into multiple spectrum, what we actually obtain, we are able to find out which source has what type of characteristics. Now talking about this, not all sources have similar frequency characteristics. If you look at this is a piano keyboard, like any instruments, if you are able to appreciate music, you will know we have a low, mid and high frequencies. Typical piano keyboard, this is what you will have the middle C and the spread of it. Each instrument, each source, any particular noise signal, sound signal will have a frequency spectrum. If you take violin for example, the prominent frequency lies somewhere between 150 hertz, it goes up to close to 3500 hertz. On the other hand, if you say a bass drum, this is a low frequency side. Typically in music systems we talk about woofer and tweeter. Tweeter goes on the high frequency, woofer goes on the low frequency. We will start feeling the vibrations itself. The bass drum gives you more in the low frequency, whereas violin gives you more in the slightly on the mid and high frequency. Whereas if you see something like a jet aircraft takeoff, you have a really wide spectrum. It ranges from a very low frequency to a very high frequency. Propeller aircraft, it is more on the low frequency compared to higher one. Now look at this, it is like male and female voice. Male voice slightly goes to the lower frequency spectrum, it starts somewhere from 125 hertz, goes all the way to slightly more than 2000 hertz, whereas female voice does not go that low, but it has a slightly higher frequency spectrum than the male voice. So if you take multiple number of sources, we will be able to split what frequency spectrum they actually are emitting the sound levels. This has lot of implications, but primary implication, the sound propagation depends mainly on the frequency and the wavelength of the sound. Frequency determines the wavelength, frequency is the number of cycle, wavelength is the distance between the compressions or rarefactions. The frequency of the sound has a strong impact on the way the sound propagates. So if you have to design a, say for example a indoor acoustical design has to be done, you have an auditorium or a classroom, you have to really understand which frequency there is a prominence of sound, which prominent frequency the sound is getting emitted. Only if you know that, you will be able to give a proper treatment. Similarly for environmental noise, you want to design a noise barrier, you want to arrest the sound, you want to do soundproofing. The first idea you should have is about the sound pressure level, how much intense the sound is, and number 2, which frequency spectrum the sound is getting emitted. So if you know these two characteristics, then you will be able to effectively contain or treat the sound source. In continuation with the previous slide, I have put certain frequencies, the frequency spectrum of some of the mechanical equipment. This is octave band again. Here you find different mechanical equipment, these are associated with air conditioning system, HVAC system. It starts from fan and pump noise. Typically fan or pump noises lie in the low frequency spectrum, it can go as low as 31.5 to around 500. So imagine you want to provide treatment for a fan or pump. If you find that the fan is emitting more than desirable noise, then if you have to provide treatment, your treatment material as well as the strategy should be attending to treat the frequency spectrum between 31.5 hertz to around 500 or say 1000 hertz. This should be your area in which treatment, the material should be effective in this particular range, your treatment should hold effective here. On the other hand, if you go with dampers or diffusers, it is on slightly on the mid and partly high frequency ranges. So again the treatment that you need to give for diffusers or dampers should be on mid and high frequency ranges, you do not have to worry about the low frequency. As the frequency level further comes down, if you can see the structure bound vibrations are present here. Imagine you are in your sound system, you are going for a woofer, there is a bass drum which is being played, the woofer is really loud, then you will start feeling the vibration. This is a typical thing you notice in PA systems as well, some of the systems good and low frequency, you will feel the vibrations. These are typically structure bound vibrations when it comes to sound propagating through your building envelope or any particular structural system, you can feel it in the relatively low frequency range. Some of these things are really not audible, say for example when it goes further below 16 hertz, you will not be able to hear it, but you will be able to feel it. Instead of using a sound measurement, you will be doing vibration measurements for really low frequency like 3 hertz, 5 hertz and all that. These are not audible ranges, the audible range is between 16 hertz to primarily 16,000 hertz, sometimes to 20,000 hertz. Getting back to our example, these are the same cracker sound that we were talking about. 3 different frequency spectrums I have put, this is 250 hertz, this is at 1000 hertz, 1000 hertz and this is at 8000 hertz. Different timelines indicated in different colors. To highlight why we need this particular frequency spectrum related analysis, what you find here, at different spectrum the distribution of sound pressure level, this is sound pressure level, considerably varies. The same sound pressure level at different frequencies, you will find a considerable difference as well as with respect to time. In case you want to impose a regulation, you want to give a treatment, you want to give protect or insulate a particular system or a building, you will have to really have an understanding of which frequency spectrum the sound is getting emitted. Now we were talking about the source characteristics, now let us take a look at the receiver characteristics. We had source, path and receiver. Moment you come to receiver, that is the human ear, the human ear is not sensitive equally to all the frequencies. Let us take a frequency from 20 hertz all the way to 10,000 or even 20,000 hertz. The frequency spectrum in which the ear is more sensitive, the ear is actually sensitive to 1000 hertz and above. As it comes down below 1000 hertz, that is as you go towards low frequency, this is where you start perceiving, that is even louder sounds are perceived to be less louder. I am using a term loud, I will come to that term in the next slide, but before that imagine you have a sound pressure of 100 decibels at 1000 hertz. If you without telling you that this is 100 dB, if I am asking a set of people to ask mark how much decibel it is or to tune another source to that particular level, they will be most probably tuning it to more or less 100 decibels at 1000 frequency, 1000 hertz frequency. Imagine I am doing the same exercise at 100 hertz frequency or 125 hertz frequency, the person is going to perceive it to be 20 decibels lower than what it actually is. So you would be probably telling that this is a 80 dB sound instead of saying that it is a 100 dB sound. As you further go down in frequency, say if you go as low as 20 hertz, you are going to perceive it as just 50 hertz, 50 dB sound at 20 hertz. What actually is it 1000 hertz, the same 100 decibels, here also it is the same 100 decibels, but you will be perceiving it 50 decibels lower than what it actually is. As you go higher, there is a slight increase, that is for example at 2000 hertz, the same 100 decibel sound ear will be perceiving, a healthy human ear would be perceiving it slightly 2 or 3 dB higher than what it actually is, but they again after say 5000 to 6000 hertz it eventually starts coming down, not as low as this, slightly lower. So this particular line, this red line represents the response of human ear. This red line typically represents how human ear perceives sound. So there is a weightage factor here. If you have, as I said, if you have 100 dB, you can apply this particular curve and find out how human ear would actually perceive the sound. This is represented as A, that is what typically we call dBA. It can be written dB within bracket A or dBA. Typically it mimics how human ear is perceiving the sound. When I take an instrument, when I measure the sound level, the spectrum, each frequency I am counting, I am making a table. After that, the conventional way of doing it was, I used to apply these correction factors at each of these frequency and scale it down or slightly up to what the human ear actually will be perceiving. So keeping this in mind, a dBA scale today, the sound level meters today have a built-in filter. So if you switch from dBE to dBA, they will apply this correction factor and tell you what dBA is actually. Sound pressure again is a cumulative number, you can measure it in different frequency and then integrate it to one number, finally we call it dBA. When we are talking about different loud sounds, so sound at 100 dB at 1000 hertz versus the same 100 dB at 20 hertz, they are not equally perceived as equally loud. So we have a quantity called loudness, we know quite well about loudness. There is a chart which was proposed by Fletcher and Munson. He drew equal loudness contours at each of these frequencies, how much the equivalent sound pressure level or how equal the sound levels. So say for example this is expressed in phones, this is frequency, you have the sound pressure levels here and these are perceived to be equally loud. Say at 1000 hertz this particular say 10 dB, at 20 hertz even the 75 dB sound will be perceived to be equally loud as this particular number. So this is like equal loudness contour. In fact this A, and I did not talk about B and C weighting, these are similar weightages used for specific applications. Say if you have to work with aircraft noise, typically you refer to B weighted sound pressure level. C is more or like linear, we also refer to linear sound pressure level, that is more or less unweighted sound pressure level, there is no weightage, the actual thing is taken more or less. We refer linear as Z weighted, C weighted is also more or less equal to the linear sound pressure level, there is not much of weighting which is given. This A, B, C or other types of weightings are primarily derived as a inverse of this Fletcher and Munson loudness curves, equal loudness curve. To quickly brush up the sound pressure level, the threshold of audibility, typically you do not hear anything, there is nothing like even in a very peaceful quiet environment you will not be able to measure 0 decibel, because air itself is exerting some pressure frictions, it will cause a minimum amount of 20-25 or at least 30 dB sound will be there present in any space. Then typically a rock show you can expect as high as 110-115 dB. A railway platform when the train is stationary, again when the train moves it is different, it can go to 80-85 dBA. Pneumatic drill at I have put that at 3 meters, as you get closer or as you get farther the sound pressure varies. So we will look at the distance corrections in a little while, around 90 dBA. Typically an office environment you need it quiet, when I say quiet you will be expecting something around 35 to 40 dBA, where you are at peace, you do not get disturbed by any other sound pressure. Typical sound levels, outdoor noises like rural ambient area, it will be somewhere between 30 to 40 dBA, and as you go up airplane, at 1000-foot height, you will still be able to find, depending on the aircraft and the turbulences, it can be somewhere between 90 to 120 dB. Typical household appliances like washing machine, dryers, chainsaw is pretty, it is a high frequency, then it will also have higher sound pressure level. You have instruments within an airplane cabin, rock band, hi-fi music, cafeteria, like this is for a quick reference, there you can build it with multiple sources. What does our pollution control what does our pollution control board talk about? It gives a simple table where different areas, zones are defined, 4 different zones are defined: industrial area, commercial, residential and silent zones. Silent zone could be an hospital or a school. Limits of dBA, sound pressure level. LEQ, I will talk about EQ little while. They have given for day and night time. Typically, for example, if it is an industrial area, daytime can be maximum 75 dBA, it should not exceed 75 dBA, whereas at night time it should be slightly lower, so 70 dBA. If it is like a residential zone, daytime maximum permissible is 55, night time it should come down to 45. Say you are conducting a pro show in a residential area, typically you will not be permitted as per pollution control board rules, because you are going to produce 80 to 90 dBA sound, while the maximum permissible is 45. If it is silent zone, daytime is 50, night time is just 40 dB. So that is what the prescribed values are. Lot of outdoor activities need to comply with this. Similar simple example is, you are working for a company, there is a construction activity going on, you need to monitor the construction noise level both daytime and night time. You have to report it to Central Pollution Control Board, only then you will be given clearance for your construction. Every there is a frequency, every month, every quarter you have to be reporting this noise levels. Typically for construction highway projects, even metro operations, any train operations, these things have to be measured and reported. So we also talked about 3 other quantities. First we were talking about pressure, we also talked about intensity and sound power. Pressure we now know it is 20 log P by P reference, P reference is 2 into 10 power minus 5 Newton per meter square. There are 2 other quantities. First let us look at sound power. When you buy a speaker, typically for your music system, you will ask how many wattage, how much watts your speaker is. So this is power. We will talk about the relationship. First is sound power. So again, power in terms of acoustical terms, we will refer it as sound power level. Sound power level is 10 log W by W reference. W is a power, W reference is 10 power minus 12 watts. Again it is a relative scale. Intensity level 10 log I by I reference, again I reference intensity, reference intensity is 10 power minus 12 watt per meter square. We will come to the exposure quickly. So what does it differ from pressure and power? When you have a sound source, it is having a power. When it is emitting, there is a medium, this is source, this is path, and it can be receiver, can be an instrument or human ear. So source, path and receiver, you perceive it as pressure. A simple analogy is, you have a radiant heater, it has certain power consumption we talk about, it has certain power, it emits the heat, radiant heat, we are talking about the heat transmission, heat transfer, it emits heat and then you start perceiving it through a sensor or through your human body in terms of temperature. So this can be equated here, there is power here and what you perceive is pressure. It needs a medium. In terms of compression and rarefaction, it propagates and then it reaches you, it causes your tympanum to vibrate in your ear, which senses it as the pressure quantity. So you have a sound power, there is a source, it can be anything, say a mechanical equipment, propagates through the room and then it reaches you. So what you measure or what you perceive is a sound pressure. We refer further to it as sound pressure level. We will look at some of the relationships. So first let us take a look at how to find out the relation between sound power and sound pressure. First of all, why do we need to know this? Most of the equipment, say like I told you the speakers, when you buy it with the power rating. You have a fan, you have a mechanical equipment, you have a motor, you have a pump. Any test certificate or the data sheet will give you the sound power levels. So first when you know the power, you actually have it in the data, you have to then calculate as an acoustician, you have to calculate what is the sound pressure or sound pressure level perceived, because human is of importance, that is why we are doing this design calculations. Typically intensity is W watts per 4 pi r square. So you take a spherical propagation, you have the source here, it propagates all across. So if you take a particular area, then it will be W, if you take the whole thing, it is W by 4 pi r square. This is where you can find the intensity. Then again similarly intensity can also be said as P square, this is pressure, rho C is specific acoustic impedance, rho is a density, C is a velocity, so you get acoustic impedance here. If you equate this and this, both the right hand side, like just W by 4 pi r square, W by 4 pi r square will be equal to P square by rho C. If you take log and equate it, you will get a equation like this, LP, that is sound pressure level, will be equal to LW minus 20 log R minus 11. Here this is a sound power level, R here is a distance, and this is a constant. So what do you understand now? So if I am telling you that the sound power level of a particular pump or a motor is going to be 100 decibel, in terms of sound power level, say if it is 100 decibel, as the distance varies, you are going to get a difference in the sound pressure level. This is a negative, you have to observe this is negative sign. So as the distance increases, the sound pressure level is going to come down. As you go farther, the sound pressure level will drop down. There is a constant here. We will look at further about the sound propagation in the next module, but quickly this is a relationship. Then the next thing is, how does sound pressure relate with the intensity? As we looked at here, intensity is P square by rho C. Rho C is a specific acoustic impedance. So now you can write this as, if I want to calculate Li, that is intensity level, this will be 10 log I by I reference. This is a logarithmic scale. So if I know the intensity, I need to find out the intensity level. This will be I by I reference. We know that I reference is 10 power minus 12. This is a number here. I reference is 10 power minus 12. Then this equation will become P square by rho C I reference. Let us keep the I reference here. So this will become P square by rho C I reference. If you write it off, you can term this whole thing as a constant called K, which will be equal to rho C I reference by P square reference. This is intensity, reference intensity, this is P square reference, that is your sound pressure reference, reference sound pressure. This is termed as K. Take a negative sign, this becomes inverse of it. Now we know both P square reference as well as we know I reference. P square reference is P reference is 2 into 10 power minus 5. So if you substitute, you will get the number 400. The only thing left is rho C. If you want to substitute value for rho C, you will need the pressure as well as temperature. Let us take air as a medium. At typical atmospheric pressure, let us take a temperature around 39 degrees. You get a rho C value, this can be calculated. Rho C value is around 400, that is the acoustic impedance provided is 400. While the temperature reduces, you get around 412, the impedance increases. So if you substitute both these values, say let us take first 400, if you substitute 400 here, is already 400, this will become 1, so the whole thing is 0. Now Li will be equal to Lp, that is sound pressure will be equal to intensity. Even if the temperature drops down, the rho C value, impedance value goes up, you are getting 412. If you substitute, you will get something around 0.01, which is negligible. If you take logarithm, it will be a very negligible number. Even then, sound pressure will be more or less equal to sound intensity. The relation between power and intensity, similarly, you have sound power level is W by W reference, W is the sound power by W reference, again 10 power minus 12. this W reference, W can be expressed as I intensity into surface area. If you substitute this, this will become, so you substitute this number here, it will become I by I reference into S. So this becomes plus 10 log of S by S reference. So this will be surface area by reference surface area. If you take reference surface area as 1 meter square, typically if you say this particular patch is 1 square meter, then this will be equal to Li, that is sound intensity plus 10 log of S. So indirectly what it means, if the surface area is 1 meter square, then sound intensity will be equal to sound power. So this basic relation between sound pressure, sound power and sound intensity we have to be remembering. The last thing is, how do you add or subtract sound power levels? So you have 2 fans, 2 pumps, we will look more about decibel additions, but the quick thing to look at, you have one sound power level, the second sound power level, 10 log W by W reference, say you will have W1 and W2, so you can find out 2 levels, then you subtract it, which ideally means in logarithm it will be W1 by W2, W1 minus W2, this is reference, so finally W1 by W2. So with this ratio you will be able to find what is the difference between LW1 and LW2. So as a part of this session we looked at 3 important things. One is we talked about basics of sound waves, their propagation, then decibel and frequencies levels, what is the decibel scale, why do we need it, and then what is the frequency spectrum, how to calculate the limits of frequencies and how common sounds have their frequency spectrum, and at last we looked at 3 relations, that is the relation between sound pressure and power, sound power and intensity, and how they relate to each other. Thank you.